In the previous video, we talked about the chi-square distribution and how chi-square is the sum of squared deviates that are sampled from the unit normal. So in this side, or the second one, we're going to talk about the F distribution. And you can think about the F distribution as the ratio of two variance estimates. So we've got variance 1, variance 2, and this guy estimates the variance in the population here, and this guy estimates the variance in the population here. We can take the ratio of these two things. If we were to do this over and over again, we would get the F distribution. Now technically, we would get F distribution if the variance is the same in these two things. Okay, so under the null hypothesis that there's no difference, you'll get an F distribution here. F distribution is also, and from a theoretical standpoint, this is probably closer to the truth. It is the ratio of two chi-squares, each divided by its degrees of freedom. So here we've got chi-square with degrees of freedom 1 divided by degrees of freedom 1. Here we've got chi-square with degrees of freedom 2 divided by degrees of freedom 2. So this is a sum of squares divided by degrees of freedom. That's a variance, or a variance estimate. In our applications, V2 here on the bottom is going to be larger than V1. So this is going to be the degrees of freedom within an analysis of variance, or the number of people minus 1 or 2 or 3, some number of people in regression models. And this is going to be for the model, so the number of cells or the number of independent variables or something like that. So typically, in our stuff where we're doing your garden variety statistical applications, V2 is going to be bigger than V1. And if that's the case, then the mean of this thing, that when you do the sampling distribution, the average or expected value of that sampling distribution will be V2 divided by V2 minus 2. So it's about 1. It's close to 1. The F distribution, the shape of that thing, depends on two parameters, V1 and V2. These are the degrees of freedom 1 and degrees of freedom 2. Shape of F changes when you change these values. The range is 0 to infinity, and it's shaped a bit like chi-square, so you have this sort of skewed distribution. It's capped at the bottom like chi-square with 0. You can't get a negative. If you get a negative value, there's something wrong in there. Something went wrong. Your calculations are off. The F tables show critical values for degrees of freedom in the numerator and degrees of freedom in the denominator. The F tables are one-tailed, so you'll see the upper right, the high end of the tail. You can figure two-tailed, but generally you don't, so we won't. All right, so here's your conventional F table, part of it. F tables get to be much larger than this, but I just want to show you how to read it in case you need to use it. Generally we don't, because the computer does all this stuff for us now, but here's the numerator. The top value, these in analysis of variance, that will be degrees of freedom between. It goes through 1 through 5 here. And then we have the degrees of freedom within, so that's for the denominator. And in analysis of variance, that would be within. So the way you read this table is you want a value, for example, alpha is 0.5 with 3 and 12 degrees of freedom. So 3 and 12 degrees of freedom. At the top, that's 0.5. The value is 3.49. If we use the 0.1, we would have to beat 5.95. So these are the critical values, or quantiles, of the F distribution. Okay, so we can apply F for very many things, but one thing we can do with it is to test hypotheses about variances. So suppose that we are considering whether variance in one group is smaller than the other against the alternative that one's bigger than the other. So the alternative is variance in group 1 is bigger than the variance in group 2. So group 1 could be men and group 2 could be women, and the difference could be height. So we know men are taller on average, but we might hypothesize that not only are men taller, but they're more variable. So the average deviation from the mean is bigger for the men than for the women. Okay, so now when I say average deviation, of course I'm using that loosely because we're talking about squared deviations here. All right, so this is a one-tailed hypothesis. And let's say we sample some data. We've got 16 guys with the variance of 5.8, and the women have a variance of 1.7. There's also 16 of them. If that's the case, then for both groups, degrees of freedom would be 15, n minus 1. And our sample value of f would be variance of one over the variance of the other. That's 5.8 over 1.7. And that gives us an obtained or observed value of f of 3.41. So we want to compare that obtained f to the critical value of f, which is that 95th percentile. And if we go to f table with 15 and 15 degrees of freedom, which was not on the table that I showed you, but if I showed you an expanded table, you could find it. For alpha 0.5 and the upper tail, critical value is 2.4. So our actual value is 3.4, and that's bigger than 2.4, which was the value to beat. So we can say the result is significant. Looks like the variance is bigger than for the women in terms of height. So you should put the larger variance on the top, especially if that's the thing that you hypothesize to be bigger. And then you got the upper right tail, or the upper value, the right tail, is what you want to compare it to. Okay, our code for the F distribution. So here's quantiles for the 95th percentile with 3 and 12 degrees of freedom. That's 3.49. Same deal if we're going up to the 99th percentile with 3 and 12, that's 5.95. If we have a value of f of 15, so now we're going from quantiles to probability. So we have a value of 15 and 3 and 12 degrees of freedom. We're at 0.9998, and the p-value that you would report for that would be 1 minus the probability of f for an obtained value of 15 with 3 and 12, which would be 0.0002, which is 1 minus that. All right, so 3.49, 5.95. You see 3 and 12, 3.49, 5.95. Those are the values that you get from the computer, and they match up with what you see in the table. So some of the applications of f. So I showed you the test for equality of variance. We're going to get to analysis of variance pretty soon, and then we're going to use f to test for differences in means. We're going to use f for tests in regression models. So we might want to predict grade point average from SAT scores, and when we do that, we'll get an R-square that indicates the proportion of variance accounted for. We'll test that R-square value using f. We might want to see whether personality attributes improve the model, so lets us predict GPA better or above and beyond SAT score. So we add in conscientiousness and curiosity and agreeableness, say, and we want to test whether that R-square increment is significant, and we'll use f for that. So we're going to use f a whole bunch. All right, relations among the distributions. So relations among the children of the normal. That's why when you see this, that's why I call them the children of the normal. So chi-square is drawn from the normal. So you've got the unit normal, which is a mean of 0 and a variance of 1. And we take those things and those deviates, we square them, and we add up as many of them as we want. So the number of them that we add together is the degrees of freedom for chi-square. F is the ratio of two chi-squares, each divided by its degrees of freedom. So that's the ratio of two variances. Chi-squared divided by its degrees of freedom is a variance estimate. Sum of squares divided by degrees of freedom. Okay, so when we get to analysis of variance, you get the sum of squares divided by degrees of freedom, and those are variance estimates. Turns out that f equals t squared. So when you do students t, you're testing the mean difference between two groups. If you take the value of t that you get from that test and square it, you get an f with 1 degree of freedom in the numerator. So t squared with v degrees of freedom is equal to f with 1 and v degrees of freedom. So they're all related. They're all relatives. So if you're by yourself, you can talk to yourself in the mirror, perhaps, or if you're sharing some popcorn or something with somebody, you can ask them these questions. How's f related to the normal? How is it related to chi-square? Suppose we have two samples and we want to know whether they were drawn from population where the variances are the same. Sample 1, we've got 50 people, we've got a variance of 25. Sample 2, we have 60 people, we have a variance of 30. So how can we do the test? And what will we conclude for these data? Are these believably drawn from the same population? Or should we say, no, I don't think so. I think they came from different populations. What's the answer? Okay, so you want to pause the video and answer these questions, and then you want to turn it back on and find the answers. Okay, so now I'm going to F distribution, and I'm going to run the clearing part. Okay, so my console is now clear. Here's showing you what R does when I ask it for the quantiles for F. I want the 95th percentile with 3 and 12 degrees of freedom, and you can see that's 3.49. And the 99th percentile with 3 and 12, that's 5.95. And where is... Let's go backwards a little bit. All right, so 3.49, 5.95. With 15, value of 15 with 3 and 12, I get 0002. And there's 9998, which is there. And if I subtract that from 1, I get 0002. All right, so slide computation. Let's run that. Let's see. Okay, so I have 16 people and 5.8, 16 people and 1.7. So here I have 16 people with 5.8, 16 people with 1.7. I compare the variances. So my sample F, my obtained F is 3.41. Then I ask for quantile for 0.95 for degrees of freedom 1 and degrees of freedom 2 here, which would be, well, I guess it is, yes, 16 and 16, so it's 15 and 15. So the F value to beat is 2.4. I've got 3.4, which is larger than the critical value. If I compute the p-value, I get 0.1, and it is less than 0.5. It's significant because 3 is bigger than 2. All right, so that's the one that I did here. I've got 3.41 and 2.40, and so you can tell that the result is significant from there. But I didn't compute a p-value here. And finally, the exercise. Let's run that. All right, I've got group 1 has 60 people. Degrees of freedom for 1 is 60 minus 1. Variance is 30. For group 2, I got 50 people, 49, 25. Obtained F is variance 1 over variance 2. Yep, 1.2. Okay, so the F value is 0.95, degrees of freedom 1, degrees of freedom 2. That value is 1.58. Well, 1.2 isn't bigger than 1.58, so it's not going to be significant. If I compute the p-value here, it's 0.25, which is bigger than 0.5, so I don't have a significant difference. So here we just talked about how F is related to the normal and to chi-square. So you've got the ratio of 2 chi-squares, each divided by its degrees of freedom, and each chi-square is related to the normal by being a sum of these squared deviates from the unit normal. And we just did the 2 samples, and for these data, the best conclusion for these data, we can't reject the hypothesis that they were drawn from a population that has the same variance across both samples.